Across the western United States and the Canadian prairies, water is being extracted from the ground at a rate that mathematically exceeds natural precipitation recharge. This structural deficit creates severe compounding failures. As the water table drops, agricultural soil dries to dust, and catastrophic wildfire corridors creep directly into dense suburban zones. The sheer volume of lost water is written on the canyon walls of major dammed valley reservoirs, marked by stark white mineral bathtub rings. In the fields above, this missing water translates into withered stalks and compromised baseline agricultural yields. Current policy treats these events as isolated, unpredictable disasters, requiring debt-funded emergency relief. But water scarcity is a solvable thermodynamic equation. We can convert this deficit into a self-funding asset through a closed, cascading industrial loop. Energy costs are the primary barrier to continental hydration. By utilizing industrial symbiosis, we remove the financial weight of both manufacturing and distribution. Historical precedent disproves the belief that large-scale inland water conveyance is economically impossible. In the mid-20th century, Israel faced severe water scarcity. Today, it operates with a structural water surplus. This surplus is generated by massive reverse osmosis desalination facilities stationed along the Mediterranean coast, seen here channeling highly pressurized processed seawater. This animated map details their reversed flow model. Desalinated coastal water is pumped inland, routed directly to replenish the Sea of Galilee. Once the lake's volume returns to baseline, surplus water is exported to neighboring territories. The result is the physical restoration of a natural lake and its surrounding agricultural zones. Israel proves that pairing coastal desalination with 90% wastewater recycling creates national water security. This scale comparison illustrates the challenge of bringing that model to North America. Overlaying the Israeli water carrier network onto the western United States reveals a massive distance gap. Bridging this transcontinental gap requires manufacturing thousands of miles of high-pressure, fiber-reinforced distribution conduits. This process creates an extrusion bottleneck. Forming these pipes requires melting raw plastics through heavy industrial steel barrels, maintained between 175 and 260 degrees Celsius. Currently, factories draw this massive thermal load directly from the public electrical grid. Paying standard grid prices for industrial heat immediately bankrupts any attempt at large-scale water conveyance. To build transcontinental water networks, we have to completely decouple the pipeline manufacturing process from public energy markets. We achieve this through the coal waste heat recovery system, an architecture built entirely on industrial co-location. We capture the data center's 40 to 60 degree waste heat. This enters a preheating chamber to warm reclaimed urban plastic and glass. An industrial heat pump then spikes this stream to the critical 260-degree threshold required by the extrusion barrel. The plant sources raw plastic and glass directly from city waste streams. Removing these materials from the municipal system yields disposal credits that optimize the first mile of collection, turning waste into a subsidized raw material. By upgrading free industrial waste heat, we bypass public utility rates and eliminate the primary capital expenditure of macro-scale pipeline infrastructure. However, to maintain profitability, pipeline manufacturing must run continuously, requiring high-grade heat through the night when local solar power drops offline. Sand batteries are integrated into the architecture. During peak daylight, excess electricity from local solar canopies routes into a silo of low-cost silica sand, heating it to 600 degrees Celsius. At night, heat exchangers draw this stored energy back out to maintain continuous plant operations. Built from crushed rock and simple insulation, this thermal storage costs only 10 to 20% of a comparable lithium-ion chemical battery. Sand batteries provide the manufacturing process with non-degrading, 24/7 thermal independence. This storage system also solves a critical flaw in the remote electrical grids routed along the pipeline path. Because solar arrays lack physical spinning parts, they provide no mechanical inertia. This leaves remote grids highly susceptible to sudden voltage fluctuations and blackouts. We stabilize those grids by pairing sand batteries with conventional steam turbines. Heat from the sand battery keeps the turbine spinning in a synchronized state, creating a physical spinning reserve that smooths out the chaotic grid waveform. To close the efficiency loop, the exhaust steam leaving the turbine is recaptured and used to run local industrial water heating. The physical thermal mass of the factory transforms it into a dynamic grid stabilizer for the entire surrounding region. The engineering framework is completely recursive. Waste heat extrudes pipes, the pipes convey desalinated water inland, and the thermal storage powering the operation stabilizes the local power grid. When routed inland and injected into dying aquifers, this system restores regional water tables, supports commercial aquaculture, and eliminates the dry conditions that fuel catastrophic wildfires. The physics and economics of this process remain identical across international borders. We can apply the exact same architecture to capture solar waste heat in the Atacama Desert, building heavy-duty pipelines for Chilean copper mines. It works for hydrating India's rapidly depleting agricultural interior, while simultaneously relieving extreme water stress in densely packed coastal hubs. Or it can be used to pump water 50 miles inland, saving crops from collapse across Guatemala's steep dry corridor. Regional water scarcity is a solvable industrial variable. By utilizing industrial symbiosis, we can rehydrate the landscape and achieve high profitability within the same engineering loop.
But what it actually gives us is a masterclass in how we can profitably solve drought and wildfires. We aren't just talking about burning through billions of taxpayer dollars to fight nature anymore. We're talking about intelligently engineering systems that actually pay for themselves.
So here's our game plan for today. We're going to cover 4 main steps. First up, engineering valley lakes. Second, aquaculture and ecotourism. Third, rethinking agricultural subsidies. And finally, the 2-tier fire defense. Let's get right into it.
Starting off with Section 1, Engineering Valley Lakes.
If we're going to solve drought and fight massive fires, we absolutely need strategic water reserves. But let's be real, digging giant new reservoirs from scratch, that is impossibly expensive. So this framework offers a really elegant workaround, using what the landscape already gives us. We're talking about pumping water into natural contour-dammed valleys. These basins are specifically engineered to hold a vertical depth of 30 to 50 plus feet. It's kind of like turning an existing valley into a massive, ready-to-go water battery, just waiting to be activated. And when you engineer that specific 30 to 50-foot depth, something really cool happens. Natural thermal stratification. The water literally divides itself into 2 perfectly utilized, distinct zones. Up top, you've got the warm surface layer, the epilimnion. This zone is tailor-made for boating, ecotourism, and giving aerial firefighting planes a wide surface to scoop water. But down below, separated by a natural barrier, is the hypolimnion. This is a cold, abyssal bottom layer powered by solar aeration. And it turns out it's absolutely perfect for freshwater cod aquaculture. You're basically getting 2 completely different ecosystems stacked right on top of each other.
Moving right along to Section 2, Aquaculture and Ecotourism.
Now, to make this whole thing economically self-sustaining, we need to look at that cold bottom layer we just talked about. Enter the burbot, also known as loda loda. This fish is actually the only true freshwater member of the cod family. It naturally thrives in freezing northern waters, and it's highly prized. People actually call it the poor man's lobster because the white meat is so firm and sweet. Plus, it yields a super valuable vitamin-rich liver oil. Raising these fish creates a high-margin commercial food yield right at the bottom of our engineered lakes. And the efficiency here, it's just staggering. We're talking about an 80 to 90% reduction in fuel usage. That's right, harvesting these fish inland takes 80 to 90% less fuel than your traditional open ocean North Atlantic trawling. Those huge ocean trawlers burn thousands of gallons of marine diesel. But out on these inland lakes, you can use standard workboats or, hey, even winter ice fishing. It keeps overhead ridiculously low, brings in serious profit, and directly boosts the local economy. All right, shifting gears to Section 3, rethinking agricultural subsidies. For this massive blueprint to work across North America, we've got to rethink agricultural policy. Historically, the government has used legacy fallow payments. That literally means paying farmers a flat fee to just do nothing, to passively idle their land. Financially, it's just a deadweight expense. The new proposal flips this on its head with active water and soil conservation credits. Instead of paying for empty fields, this model actively rewards farmers for making verifiable improvements to water and soil health. And the best part? Doing this requires zero net budget expansion. You're probably wondering, well, how do we do that without spending more money? The plan simply repurposes existing conservation funds from the USDA and Agriculture and Agri-Food Canada. It builds right on top of current working lands frameworks like EQIP and CSP. Farmers get direct tax credits, and they're rewarded for actual, verifiable performance-based yields. The big takeaway here is that by just updating how we use existing budgets, we can fund a resilient, drought-immune landscape without asking taxpayers for a single extra dime. And finally, that brings us to Section 4, the two-tier fire defense. This is really the climax of the whole framework. It deploys a brilliant two-tiered defense system that pairs immediate fire suppression with proactive hydration. Step 1 is establishing deep reservoir aerial scoop bases, and Step 2 uses topsoil remoisturization to build living fire breaks. Let's dig into exactly how these two layers interlock to stop wildfires in their tracks. Think about the logistics of fighting a massive forest fire. The biggest handicap is the time it takes for aircraft to fly back and refill their tanks. But if we intentionally position our engineered lakes right along high-risk timber corridors, we give amphibious aircraft, like those massive super scoopers and heavy heli-tac fleets, tactical scoop bases every 1 to 1.5 miles. That drops turnaround refill times from hours down to literally minutes. You can unleash rapid-fire, high-volume water drops to squash small spot fires way before they ever explode into firestorms. So the planes handle the active blazes from the sky, but Step 2 is all about stopping the fires from ever igniting on the ground. Water is gravity-fed through upcycled HDP pipes into contour swales, which constantly recharges the shallow water table. From there, deep-rooted trees like the bur, oak, and black walnut do the heavy lifting. They act as massive biological pumps. Through hydraulic lift, they physically pull that deep subsurface moisture upward, perfectly hydrating the forest underbrush around them. And that brings us to a magic number: 30%. The main goal of these biological tree pumps is to keep the brush's fuel moisture content above 30%. Why? Because at that specific moisture level, physics simply takes over. Flying embers physically cannot ignite the vegetation. It's just too wet. By keeping the soil and the brush saturated, we're creating permanent, self-sustaining living fire breaks that naturally snuff out fires before they start. This two-layer hydrological defense completely eliminates the need for the endless, exhausting cycle of manual clearing and prescribed burns. To put it in perspective, right now, those manual methods cost taxpayers a staggering $1,000 to $4,000, sometimes even more, for every single acre. We'd be replacing a massive, draining taxpayer expense with a natural, self-funding symbiosis. Which leaves us with a really big question to chew on. Is it time we stop fighting nature and start engineering symbioses to profitably resolve our climate disasters? Cole's framework makes a compelling case that we don't have to just sit back and accept drought and fire, and we definitely don't have to go bankrupt trying to fight them. By utilizing natural contours, smart aquaculture, and modernized agricultural policies, we can actually build landscapes that both protect and fund themselves.
If you've been paying any attention to the news lately, you've probably heard the same gloomy story over and over. North America is facing an inevitable, slow-motion water catastrophe. We hear about drying rivers, shrinking aquifers, devastating wildfires, and the general consensus seems to be that, well, we just have to brace for impact. But what if we completely flipped that narrative? Today we're unpacking an incredibly ambitious blueprint by Dorian Scott Cole. It's a macro hydrological and industrial symbiosis framework that aims to not just solve drought and wildfires across North America, but to actually do it profitably. It's a fascinating, deeply structured approach, and we're going to break down exactly how it works.
Okay, let's dive into this with the core thesis that drives this entire framework. Cole argues that water scarcity is not a state of nature. It is a failure of fluid dynamics, material management, and thermodynamic integration. I absolutely love this perspective because it shifts the blame away from Mother Nature and points it right at our own engineering and resource management. It basically suggests that we don't have a lack of water, we just have a massive lack of imagination and infrastructure.
Section 1. The water scarcity myth.
And this brilliantly illustrates the massive geographic scale we're talking about here. The traditional view is that drought is just something we have to endure, right? But instead of accepting that, this framework proposes utilizing the waste generated by our modern digital lifestyle to build the ultimate solution. We're looking at a system that begins at the ocean with coastal desalination and then literally pumps that fresh water thousands of miles inland. It moves through the Colorado River Basin, which feeds Lake Mead, stretching all the way up into the Canadian prairies and pushing east to the Ogallala Aquifer beneath the American Midwest. Now, if pumping desalinated water deep inland sounds a bit like science fiction, remember that Israel has actually already pioneered similar models on a smaller scale. We're just talking about scaling it up to fit the entire North American continent.
Section 2. Following the water inland.
So think of this new infrastructure not just as pipes and pumps, but as the physical arteries of our landscape. Buckle up because here's our roadmap for this journey. The framework is built on 5 major structural assets. First, we start at the ocean with coastal desalination outfalls. Second, the water travels through piping and energy canopies. Third, it reaches the high plains for aquifer injection. Fourth, it pools into dammed valley reservoirs. And fifth, the whole shebang is integrated with corporate co-location. This isn't just a simple pipeline, it's an interconnected highway of resources where every single stop actually pays for itself.
Consider the stark contrast between our current system and this new framework. In our current model, desalination creates toxic brines, our everyday consumption creates a mountain of plastic waste, and our internet usage creates excess data center heat. Usually, we spend billions just trying to throw these things away. But in this upcycled model, that toxic brine becomes battery lithium, that waste plastic becomes solar-powered pipes, that excess heat translates into highly valuable ESG credits. The sheer brilliance of this framework is that it takes our biggest environmental liabilities and transforms them into highly profitable revenue engines.
Section 3. 5 engines of profit.
That whole concept of industrial symbiosis leads us right into the core financial mechanics of the blueprint. Our first stop is the coast. Typically, the leftover brine from desalination is incredibly salty, highly toxic to marine life, and dumping it is a major environmental headache. But instead of dumping it, this node commercially extracts lithium and cobalt. And as we know, those are absolutely critical for the surging electric vehicle battery market, a sector that is desperate for domestic supply chains. It also extracts magnesium for eco-concrete. So before a single drop of water even moves inland, the system is already generating massive revenue by supplying the green energy and construction sectors. Talk about a win-win.
Okay, now the water actually has to travel. For Node 2, we have the piping and energy canopies. And these aren't your standard run-of-the-mill steel pipes. They're made from upcycled mesh high-density polyethylene, essentially repurposed consumer plastics. Because they use waste heat for manufacturing, meaning they don't have to burn new energy just to melt the plastic down, they boast a zero thermal manufacturing cost. But it gets even better. These pipelines are covered in solar panels and backed by sand battery storage. They generate their own renewable energy to pump the water, and they actually produce a surplus. That excess solar and wind power is then sold right back to local utility substations, so the pipeline itself acts as a massive, sprawling power plant.
Arriving at our third node, the water reaches the heartland. The Ogallala Aquifer, which sustains so much of U.S. agriculture, is currently drying up at an alarming rate. This system uses managed aquifer recharge to inject the desalinated water deep underground, actively restoring the water table. But again, it's monetized. The system sells this agricultural water to High Plains farms and cattle operations. And to make sure this is actually sustainable long-term, these sales are tied to mandatory drip irrigation rules. This prevents the exact kind of wastefulness that caused the aquifer to deplete in the first place.
Our fourth node involves the surface water, dammed valley reservoirs. These act as hypolimnetic cold water refuges. Actually, scratch that. Let's just call them deep, naturally chilled pools of water that are absolutely perfect for fish. And they pull quadruple duty as revenue generators. They host commercial aquaculture, specifically for burbot, which is often called freshwater cod, and tilapia. But on top of the commercial fish harvest, these reservoirs are developed for public ecotourism, generating really consistent income through boating slip leases and sporting permits. It perfectly blends ecological restoration with a thriving, fun, recreational economy.
Finally, we reach the fifth node, corporate co-location. So the crucial point is, this is where the tech industry foots the bill. By co-locating huge data centers and power plants right alongside this water infrastructure, the system captures their massive amounts of waste heat to drive the water purification and manufacturing processes. In exchange, big tech gets to buy high-permanent Scope 1 and Scope 2 carbon offsets, as well as social impact ESG credits. And here's the kicker. The revenue from these credits is specifically earmarked to underwrite youth workforce development and student apprenticeships. It ensures the next generation is fully trained to operate this massive new grid.
Section 4. The billion-dollar payoff.
So we've seen the engineering, and we've seen the social benefits. But how do you get the financial world, the private equity guys, to actually build this? Saving the environment can't just be a charity case. It has to make real economic sense.
Well, the master system is projected to yield between $5.2 and $7.1 billion annually. And this isn't imaginary, speculative money. This is hard revenue generated from raw commodities like lithium and magnesium, the commercial fish harvests, massive land appreciation around the new reservoirs, recreational leases, and utility revenues from all that excess solar power we talked about earlier.
And because that annual yield is so remarkably high, the math on the capital investment becomes incredibly attractive. The framework estimates that it would only take 12 to 15 years to achieve full capital payback on the infrastructure bonds required to build this. Let me put that into perspective for you. In the world of massive civil engineering and private equity, a 12 to 15-year payback period on a project that literally secures an entire continent's water supply, that is an absolute home run, especially considering most civil projects of this scale take several decades to even come close to breaking even. It completely cements the economic viability of the entire blueprint.
Yes, for sure, the finances work, but the ultimate closed-loop reality it presents is what matters most. Now, what's really interesting about this slide is that it shows this isn't just about delaying a crisis, it's about fundamentally reversing it. By anchoring this system to private equity and youth development, we achieve a physical reality where the Ogallala Aquifer is fully restored, Lake Mead is refilled, the chronic, bone-dry conditions that fuel those devastating wildfire hazards are systematically eliminated. Ultimately, this architecture secures the agricultural future of the United States and Canada for generations to come.
It completely changes how you look at the landscape, doesn't it? We've just walked through a framework that takes the waste of our modern world and spins it into the very arteries of our survival, paying for itself every single step of the way. Which leaves us with a pretty profound question to consider. If something as catastrophic as water scarcity is truly just a failure of management and thermodynamic integration, what other so-called natural limits are we facing today that are simply waiting for a better blueprint?